Have you ever heard of a place called Giant's Causeway? It's a stretch of land on the north coast of Northern Ireland, which is renowned for its unique arrangement of rock formations. These formations are actually basalt columns, which are naturally formed as hexagonal in shape. When you see this landscape, it's hard to believe that it was created by nature. So much so, local folklore came up with the legend where an Irish giant called Finn McCool, what a cool name, right? Laid these hexagonal stones as a passage over the sea to meet a Scottish giant who challenged him to a fight. An easier option to understand, I guess, if you're not a geologist. So you might be wondering what this geological wonder has to do with the liver. Well, on a histological level, the structure of the liver also has a hexagonal arrangement, just like the basalt columns of the Giant's Causeway, and is just as, if not more, fascinating. So if you want to find out what's so special about the liver histology, stick with us, because that's exactly what we're talking about in today's tutorial. So before we literally get into all the tiny details, let's have a quick rundown of all the topics we're going to tackle today. We'll start our tutorial on liver histology by looking at the gross anatomy of the liver and the histological slide that will feature throughout our tutorial. This will be followed by the elements of the stroma, which is the non-functional and structural parts of the liver. Then we'll speak about the arrangement of the liver's internal vasculature, as well as the parenchyma or functional tissue of the liver. We will then talk about the arrangement of lymphatic vessels and the biliary tree in the liver. Finally, with that information in mind, we'll be able to appreciate the different methods of describing the structural organization of the liver. And we'll finish up with some clinical notes, which will put liver histology into perspective. Before we look at the microscopic structure of the liver, let's quickly remind ourselves a little about its gross anatomy. The liver is an accessory digestive organ located mostly in the upper right and partly in the upper left quadrant of the abdomen. The liver is the second largest organ of the body after the skin, its weight coming in at around 1.5 kilograms, so about the size of a small chihuahua. And it's no wonder it's so large, considering its wide range of functions. It is said to have around 500 different functions, but the main ones include filtering and degrading toxic substances coming from the digestive system, maintaining blood glucose levels, the uptake, storage and distribution of nutrients and vitamins, and of course its exocrine function of bile secretion. Note that this is a very brief summary of such a complex organ, but worry not, if you want to know more, we have detailed videos and articles available on our website. Now allow me to introduce you to the histological section we'll be using for the majority of our tutorial today. You've probably already recognized that the section has been stained with an H&E stain. Most of them are, right? H&E stands for hematoxylin and eosin, the two dyes associated with this staining method. Hematoxylin is a basic dye and stains basophilic structures such as cell nuclei purple, whereas eosin is an acidic dye and stains acidophilic structures such as the cytoplasm red or pink. On low magnification, a human liver looks a bit like pink mush. But if you zoom in, it has one of the most fascinating tissue arrangements of the whole body. The liver needs some structures to hold it together and give it its shape. So first up, we're looking at the stroma, or non-functional part of the liver, which does just that. Let's start by looking at the outermost part of the liver, its fibrous capsule, also known as Glissen's capsule. The fibrous capsule extends into the parenchyma to form the interlobular septa of connective tissue. These septa divide the liver into the hexagonal lobules we mentioned earlier. The connective tissue contains nerves, blood and lymphatic vessels, as well as bile ducts. The liver also receives structural support from reticular fibers. Reticular fibers cannot be seen with H&E staining, but the reticulin-stained micrograph shows you what they look like. These fibers form a meshwork or scaffold, which supports the cellular liver tissue. Let's move on now to our next topic of the day, the vasculature of the liver. Now, the blood supply to the liver is somewhat unique in that it has a dual supply, with around 75% of the blood coming from the hepatic portal vein. This venous blood comes directly from the digestive system, which means it is oxygen depleted, but contains nutrients and toxins absorbed during the digestive process. The remaining 25% comes from the hepatic artery proper, which is a branch of the celiac trunk and carries oxygenated blood. Both of these vessels enter the liver at the hilum, also called the porta hepatis. Inside the liver, both the hepatic artery proper and hepatic portal vein branch out to supply the subunits of the liver, which are known as hepatic lobules. These branches generally run together and are easy to find and identify. Let's take a closer look. Inside the liver, branches of the hepatic artery proper and hepatic portal vein are easy to find and identify due to the reason that they travel together, along with another type of duct, in what is known as the portal area or field. In our histology micrograph, we can see all three vessels here surrounded by connective tissue. Highlighted in green is an interlobular artery, which originates from the hepatic artery proper. It is identifiable by squamous endothelial cells around the lumen and a thick tunica media. Running alongside the interlobular artery is an interlobular vein, which, as its name suggests, originates from the portal vein. It is also lined by squamous endothelial cells, but is usually larger and lacks that well-defined tunica media that we saw with the interlobular artery. And finally, the interlobular artery and vein are accompanied by an interlobular bile duct, which is lined by cuboidal epithelium. We're going to speak a little bit more about this a little later in the tutorial. So as I mentioned, these vessels travel in what is known as the portal area, or portal field, and are collectively known as a portal triad. This term is not always seemingly accurate in reality, however, as there normally is at least one small lymphatic vessel travelling with the portal triad, and you might often see more than one interlobular artery or vein, or alternatively, the interlobular artery, vein or bile duct may not be visible. As I'm sure you already know, where you have blood supply, you also have venous drainage. In the liver, each lobule has a central vein, also known as a terminal hepatic venule, doing its job. The central vein gets its name from its location, roughly in the center of each hexagonal lobule that we mentioned at the beginning of our tutorial. These veins empty into larger sublobular veins, which in turn empty into hepatic veins, which exit the liver at the hilum and empty into the inferior vena cava. The blood supply to the liver is intricately connected to its function. To understand this mechanism, we need to look at the liver parenchyma or functional tissue. The parenchyma has a rather fascinating arrangement, but can take a little work to wrap your head around. So let's break it down. Firstly, we have these strings of cells radiating from the central vein outwards towards portal triads, called the hepatic cords. They are formed by hepatocytes, which constitute around 80% of all cells in the liver. Hepatocytes are large and polyhedral, which means that they have several surfaces. For convenience sake, they are usually described as having 6 surfaces. They measure between 20 and 30 micrometers in every dimension and have large rounded nuclei. Many hepatocytes actually have 2 nuclei and are polyploid, meaning they have 2 or more sets of DNA. Do you remember when we talked about the H&E staining method at the beginning of our tutorial? Here we can see that hematoxylin has stained the nuclei purple and eosin has stained the cytoplasm pink. At the margin of each lobule, the outermost layer of hepatocytes form what is known as the limiting hepatic plate. Between the hepatic cords is an interconnecting network of capillaries, which arise from the interlobular vein and artery and carry blood towards the central vein. These structures are known as the hepatic sinusoids or sinusoidal capillaries. If you look closely, you'll even see some red blood cells in the capillaries stained bright red. Sinusoids are lined with discontinuous endothelium, which means there are large gaps between the neighbouring endothelial cells, allowing easy passage of blood plasma to and from the blood and hepatocytes. The blood plasma leaks into a small space between the hepatic cords and the capillary wall, which is known as the perisinusoidal space or the space of Dis. The space lies between the basal surfaces of endothelial cells and hepatocytes. Microvilli of hepatocytes extend into this space in order to absorb proteins and other plasma components present. Among the endothelial cells of the sinusoids are stellate macrophages, also known as Kupffer cells. They do not form junctions with the endothelial cells of the hepatic sinusoids and often extend into the lumen of perisinusoidal spaces, sometimes partially closing them off. These cells are of high importance due to their strategic position within the liver in that they are the first point of contact with materials absorbed by the gastrointestinal tract and are the permanent population of immune cells in the liver. If activated, these cells function as macrophages and are capable of phagocytosis and secretion of inflammatory mediators in order to combat antigens and other pathogens, as well as degrade various pathogens, immune complexes, and apoptotic cells present in sinusoidal blood. They are also thought to play an important role in several pathological conditions of the liver. With a similar name, but a very different function, we have hepatic stellate cells, also commonly known as ito cells or perisinusoidal cells. These cells are found in the perisinusoidal spaces, but instead of forming part of the endothelial lining, they are wedged between two adjacent hepatocytes. One of the main functions of these cells is vitamin A storage, so it will come as no surprise that in a histological section, the distinguishing feature of hepatic stellate cells are fat vacuoles in their cytoplasm. In certain pathological conditions, the hepatic stellate cells lose their ability to store vitamin A and start producing collagen instead, filling the perisinusoidal space and resulting in liver fibrosis. In cases of steatosis of the liver, also known as fatty liver, you can also sometimes see fat microvacuoles present in the hepatocyte cytoplasm. These can be somewhat similar in appearance to the hepatic stellate cells we just looked at. However, a steatotic hepatocyte will normally retain its typically large, dark nucleus. You can see in this micrograph many white spaces, which are where larger fat macrovacuoles were present among the hepatocytes. Accumulation of these fat deposits is very typical of fatty liver. Now, before we wrap up this section of the tutorial, something that we need to wrap our head around is the arrangement of hepatocytes. If you picture them as little cubes, two opposing surfaces will be facing the perisinusoidal space. These are the perisinusoidal surfaces of hepatocytes, covered in microvilli, which increase the surface area for the exchange of materials. The remaining four surfaces face neighbouring hepatocytes and are involved in bile transportation, but we'll look at it in more detail later on in this tutorial. That concludes our section on the liver parenchyma, so let's move on to our next topic of the day, which is lymphatic drainage. We've already talked about how exchange of materials happens in the perisinusoidal space, between hepatocytes and sinusoidal capillaries. Well, not all plasma, or the liquid component of the blood, gets taken up by liver cells or returned to the bloodstream. The remaining plasma drains into what is known as the periportal space, or the space of Moore. It is a space between the connective tissue of the portal area, where our portal triad is located, and the hepatic limiting plate, facing the portal canal. That means the lymph flows in the opposite direction to blood in the liver. From here, the lymph enters small lymphatic vessels travelling with the portal triad. It then drains to progressively larger lymphatic vessels, eventually exiting at the hilum of the liver. 80% of the hepatic lymph goes on to drain into the thoracic duct. That wraps up the lymphatic drainage of the liver, but we can't forget the liver's exocrine function, bile production. And of course, we need a system to collect it, and that's where the biliary tree comes in. Bile production is an exocrine function carried out by the liver. To start learning about the biliary system, let's take another look at our hepatocytes. This time we're going to be concerned with the sides of the cell facing other hepatocytes and not those in contact with the perisinusoidal space. Opposing surfaces of hepatocytes bear small grooves, which form small channels known as bile canaliculi, which receive the bile that is secreted from the hepatocytes. On a histological slide, bile canaliculi can be next to impossible to make out, as their lumens are only about 0.5 micrometers in diameter, but you can be aware that they are located between adjacent hepatocytes. As the bile canaliculi transform into short, slightly larger bile canals, also known as the canals of Herring, and these are still contained within the lobule. These differ from bile canaliculi in that they are lined with a stem cell niche in addition to normal hepatocytes. This niche, which contains the progenitor cells of hepatocytes and the cells which will go on to line the bile ducts, which are known as cholangiocytes. Once again, these canals are unfortunately very difficult to identify in histological section. When the epithelium of the bile canals consists entirely of lining cells known as cholangiocytes, and hepatocytes are no longer present, they become known as bile ductules. If you haven't encountered the term cholangiocyte before, don't worry, they sound scarier than they actually are. They are just a type of epithelium present in bile ducts. Due to the change in epithelium, bile ductules are not so difficult to identify with their distinct cuboidal epithelium. These are usually found at the boundary of the lobule or within the portal area. It's important to note that some texts will not differentiate between bile canals or canals of Herring and bile ductules. Therefore, these terms are sometimes used interchangeably despite the definitions given earlier in this tutorial. Let's now talk about the interlobular bile duct, which you will remember as one of the trio we looked at earlier when discussing the portal triad. These are also lined with cholangiocytes, which transition from cuboidal to columnar as they approach the porta hepatis. The interlobular bile ducts join to form the left and right hepatic ducts, which join at the hilum of the liver to form the common hepatic ducts. It's important to note that the bile collection starts around the area of the central vein and flows towards the periphery of the lobule. So just like lymph, bile flow is in the opposite direction to the blood. Now that we've covered all of that, you must be wondering what can possibly be left to learn. Well, it's finally time to put all of the pieces together and discuss the structural organization of the liver. There are 3 different ways to describe the structural organization of the liver, and all 3 methods are identified in relation to the hepatic vessels. We have the classic hepatic lobule, the portal lobule, and the liver acinus. Let's discuss them in a little more detail, starting with the simplest one, the hepatic lobule. And I say the easiest because we're already familiar with it. It's roughly hexagonal in shape, with portal areas defining its angles, and a central vein in, well, the center. Now, in some species, for example pigs, the lobules are defined by very clear, thick septa, whereas in the human liver, the septa are either really thin or absent altogether, so you might need to spend a little longer to identify them. In our H&E section, you can see a few thin elements of septa, which we've highlighted for you now. Just as we saw previously, the hepatic lobule consists of cords of hepatocytes radiating from the center of the lobule, with a network of sinusoids between them. It can sometimes be hard to visualize histological elements as 3-dimensional structures, as we're always seeing only a flat snapshot of them. The hepatic lobule is the traditional way of describing the liver's internal architecture, as it is relatively easy to visualize. Our next method of structural organization is the portal lobule. It may require a little bit of creativity, because to define it, you have to draw imaginary lines between the 3 central veins of adjacent hepatic lobules, which form the corners. This leaves you with a portal area in the center of each portal lobule. So what's good about this method? Well, it focuses on the exocrine function of the liver, and with an interlobular duct in the center, it roughly divides the area of liver tissue which produces bile received by the interlobular bile duct in the center of the portal lobule. The last way to describe the organizational structure of the liver is arguably the most complex, but potentially also the most useful. We're talking about the smallest structural organization unit, known as the liver acinus. This unit is roughly oval or diamond in shape, with the central veins of 2 adjacent hepatic lobules defining its long axis. Its short axis is defined by the blood vessels of the portal triads that lie along the border between the same 2 hepatic lobules. This method of structural organization is all about the liver's metabolic activity and is divided into 3 zones. Zone 1, also known as the peripheral zone or occasionally as the perilobular zone, has the best vascular supply and therefore the highest metabolic activity. That means that any oxygen and nutrients, but also toxins, reach the cells in this area first. So it would logically follow that Zone 3, also known as the central zone or centrilobular zone, closest to the central vein, would receive the nutrients as well as toxins last. Zone 2, also known as the intermediate zone or midlobular zone, is not clearly defined, sits between zones 1 and 3, and has an intermediate metabolic activity. And that concludes our liver histology. But hold on, what's the point of learning it if we don't put it into a context? Let's look at some clinical notes to see why knowing the liver histology can be very useful. Today we're going to talk about centrilobular necrosis. One of the causes of centrilobular necrosis is congestive heart failure, which results in a deficiency in the amount of oxygen reaching the tissues, also called hypoxia. That means the liver, as well as other tissues of the body, does not receive a sufficient blood supply. This is where the zonation of the liver acinus we just learned comes to be super useful. The blood, which reaches zone 3, is already largely deoxygenated even with a healthy oxygen supply, so when it is lacking, this area is very clearly affected first. This manifests as ischemic necrosis, or breakdown of hepatocytes, which are replaced by these clear rounded areas which represent lipid accumulations. Meanwhile, zones 1 and 2 are typically not affected and display the usual characteristics of liver tissue. The name centrilobular necrosis is given to the condition because it affects the central area of a hepatic lobule, another example of why knowing different structural organization principles is very useful. It is a broader term describing damage with various causes. So we have a specific term for ischemic necrosis caused by hypoxia, which is cardiac cirrhosis. The treatment is focused on managing the underlying cardiac tissues, but liver cirrhosis can be managed with beta blockers and diuretics. That concludes everything we wanted to teach you in this tutorial today. But before we finish up, let's have a quick recap of what we learned. We started with the stroma, or the supportive, non-functional part of the liver. We identified the fibrous capsule surrounding it and the interlobular septa separating the liver into smaller lobules. We then moved on to learn about the unique dual blood supply to the liver, with the majority of blood coming from the hepatic portal vein and the rest from the hepatic artery proper. We then moved on to look at the small terminal branches of these large blood vessels travelling together in a portal triad within portal areas all through the liver tissue at the angles of the hexagonal lobules. We identified an interlobular vein, an interlobular artery, and an interlobular bile duct. We saw that the venous drainage takes quite a different pathway from the blood supply. The smallest unit of the venous drainage, known as central veins, were located in the centre of the hexagonal lobules. They empty into larger sublobular veins, which in turn drain into hepatic veins, which then empty into the inferior vena cava. Then came the time to look at the main functional cells of the liver, called hepatocytes. They are polyhedral cells forming hepatic cords radiating from the central vein, creating anastomosing plates of cells stacked on top of each other in hexagonal lobules. Between these plates, we saw an interconnected network of sinusoids, capillaries connecting the interlobular vessels to the central vein. Between the sinusoids and hepatocytes was the perisinusoidal space, separated from the sinusoids by discontinuous epithelium with stellate macrophages or Kupffer cells. Also in the perisinusoidal space, but wedged between adjacent hepatocytes, we found hepatic stellate cells, which are responsible for vitamin A storage. We then moved on to the lymphatic drainage of the liver. We saw that some plasma remained in the perisinusoidal space and was carried towards the periportal space of Moll, between the portal canal and the outermost layer of hepatocytes. Lymph then drained into progressively larger lymphatic vessels until it exited the liver at the porta hepatis. Then we tackled the rather complex biliary tree. Bile produced by hepatocytes was first collected in bile canaliculi. They then drained into slightly larger bile canals lined with cholangiocytes and hepatocytes, which in turn emptied into bile ductules lined with cholangiocytes only, which carried the bile to the interlobular bile ducts of the portal triad. These joined to form left and right hepatic ducts and eventually the common hepatic duct. And finally, we looked at 3 different types of structural organization which can be identified in the liver tissue. The hepatic lobule is hexagonal and widely used due to the ease with which it can be identified. The portal lobule was triangular, defined by 3 central veins and a portal triad in the middle. This arrangement helps to visualize which part of the liver produces bile that drains into the specific bile duct in the center of the lobule. Finally, we looked at the liver acinus, divided into 3 zones, which help to appreciate the metabolic activity within the liver tissue, with Zone 1 receiving the most oxygen, nutrients and toxins, and Zone 3 receiving the least. Finally, we applied the zones of the liver acinus to discuss the changes expected in the liver tissue in the case of cardiac cirrhosis, with Zone 3 undergoing ischemia and Zones 1 and 2 remaining unaffected. And that wraps up today's tutorial. Hope you enjoyed it, see you next time, and happy studying!